Hi, my name is Frederik Möllers. I'm from Saarland University in Germany, and I'm going to present my paper on energy-efficient dummy traffic generation in home automation systems. So for the overview, I'm going to start off with a short motivation. I'm going to then introduce the problem model that was actually published before, but just to get everyone on the same page here. I'm going to then present our research into constant rate dummy traffic, which means generating traffic at a constant rate, introducing dummies where needed. And then I'm going to introduce my own approach, naive exponential dummies, which aims to strike a compromise between privacy and energy efficiency. And then I'm going to finish the talk with a short conclusion. So to start with the current situation, we can see a steep increase in the presence of home automation systems in houses and apartments. Those systems are getting more and more common. They are getting cheaper. The hardware is getting cheaper, and more people start to install such systems to increase the comfort of living, to save energy, or even to increase the security. The problem with this is that many of those systems are built to be as cheap as possible, and of course, with this come a lot of security and privacy issues. There have been headlines where home automation systems have been so insecure that burglars could misuse them to gain access to the houses and so on. Previous research has also shown that these systems often introduce severe privacy issues. For example, we have shown in a past paper that one could eavesdrop on the communication in a household or on the communication from a home automation system. And here, for example, in the graph, we could reconstruct the temperature values that were measured in a room, which gives us information about the heating and ventilation habits of the user living there. Previous research has also shown that wired systems are almost as susceptible to these attacks as wireless systems. By placing small listening devices on the walls, attackers could eavesdrop on the communication over wires. So using wired systems does not protect the user completely from these attacks. Okay, on to the main matter of the paper. We assume the following attack scenario. We have a passive eavesdropper who does not inject traffic into the system, who does not compromise devices, but who just listens passively to the communication that is being received and transmitted by the system itself. The attacker has strong reception, so they are able to capture all traffic that is sent and received. They are not able to break any encryption whatsoever. And the goal is to identify user interaction, so to determine whether a user is currently interacting with the system or not. So to formalize this, we assume that the attacker observes traffic samples. So what they get is a list of, for example, timestamps, which may be annotated with any information that the attacker is able to see. For example, wireless channel information, maybe addressing metadata, whatever they might be able to see. The goal of the attacker is to decide whether a user is interacting with the system. So to formalize this, we want to quantify the probability of the occurrence of a particular traffic sample. We assume that the user is given the choice between two tasks, A and B, which may of course be possibly empty. The user has to perform one of the tasks. The attacker then captures the output of the system in terms of traffic samples, and then the attacker has to decide whether the user performed task A or task B. An intuitive special case of this is, for example, task A is the user interacts with the system by pressing a light switch, versus task B, the user does not interact with the system at all during the given time frame. The attacker then captures the traffic of the system, for example, an empty observation over a period of a minute, and then, of course, in this case, the attacker is able to determine that the user did not perform the task that where he would have interacted with the light switch, but instead did not interact with the system at all. So in a previous work, we have thus established the notion of epsilon delta private communication, which borrows concepts from differential privacy and epsilon delta private information retrieval. We have an observation O, which is basically a traffic sample, as I said. For example, a list of timestamps, a list of inter-arrival times, so the difference between two subsequent timestamps, possibly annotated with channel information whatsoever. We have two tasks, which are of which one is performed by the user, and then we measure the probability of observing a particular traffic sample in the one case or the other case. And we then state that a system offers epsilon delta private communication if this inequality holds, namely that the probability of observing a traffic pattern under the assumption that the user performs one task is less than or equal to e to the power of epsilon times the probability of observing the same traffic pattern under the assumption that the user performs the second task plus some delta. Delta is basically a constant information leakage that the system cannot completely prevent, and epsilon is an exponent to a factor by which the probabilities are higher. We have also defined special cases. For example, we have or we state that a system offers epsilon delta indistinguishability if this inequality holds for some finite fixed set of tasks T. For example, this set might comprise tasks such as pressing a light switch, unlocking a door, turning on the heating, and so on. And if this inequality holds, this basically means that an attacker can only distinguish between these tasks with some limited confidence, limited by the factors epsilon and delta. We have also defined epsilon delta unobservability, for which the inequality must hold for a set of tasks T, where for each task in this set, the complementary task must also be included, which means that if a task T, such as the user presses a light switch, is included in the set, then the complementary task, meaning the user must not press a light switch during the given time frame, must also be included in the set. This basically means that if a system offers unobservability or epsilon delta unobservability for a set of tasks, then these tasks or these interactions given by those tasks can only be inferred by the attacker with a limited probability or with a limited confidence, limited by the values epsilon and delta. Just to illustrate this, let's take a system that generates dummy messages, and we take a particular traffic pattern that an attacker captures. Now, if this traffic pattern only occurs whenever the user interacts with the system in a specific way, then the probability of observing this, under the assumption that the user interacts with the system in this way, this value determines the value of delta, because it only happens in one case and never in the other. On the other hand, if we have a sample that can be observed in both cases, when the user interacts with the system or when they do not interact with the system, then the ratio of these probabilities then determines the value of epsilon. This is why we call delta the constant privacy leakage. Now, the first countermeasure that comes to mind is, of course, generating dummy traffic. And when generating dummy traffic, the easiest way to do this is to generate dummy traffic at a rate that completely fills all links. So that means we generate dummy traffic whenever we don't have any genuine information to send, so that we have a constant data rate on all links, so that the attacker can never see whether there is genuine information being transmitted or whether it's only dummies. Now, given the definitions from before, we can rather easily prove that constant rate dummy traffic provides perfect epsilon delta private communication with epsilon and delta being 0. This provides perfect privacy because it's obvious to see that an attacker can never correctly or can never decide whether a task A or task B was performed based on a captured traffic sample. The attacker can never perform better than randomly guessing. However, constant rate dummy traffic also has its downsides, namely that it completely fills all the links with traffic. We know from many anonymity networks, for example, that they refrain from using constant rate dummy traffic because of the traffic overhead it introduces. And the main concern in home automation systems is, of course, energy efficiency. The more packets we transmit, the more energy the system consumes. And if it's a battery-powered system, which many wireless systems are, then this, of course, reduces the battery life, which means higher cost and higher inconvenience for the users who have to exchange the batteries more often. The question is now, is this intuition actually true? So is constant rate dummy traffic actually infeasible in terms of energy consumption for home automation systems? And to answer this question, we have performed 5 different simulations using 5 different models. One model was established on Wi-Fi hardware using regular laptop hardware, measuring the energy consumption of that. Then we have taken 3 specialized IoT devices with energy consumption measurements, have performed the same simulation using that data. And last but not least, we have performed our own measurements using Homematic hardware, a popular home automation system, and have performed a simulation using this data. The result of these simulations was quite surprising. We could see that, for example, in the Wi-Fi hardware case, the energy consumption that is introduced, or the additional energy consumption that is introduced by using constant rate dummy traffic, is actually negligible because the idle power consumption of the system is so high that transmitting all those dummy packets doesn't even make a difference in terms of energy consumption or total energy consumption. For the other systems, there have been varying results. For the specialized IoT hardware, the difference was quite significant. And using our own measurements, we have seen that constant rate dummy traffic here might not make sense because the energy consumption has increased by a factor of 11. That means that the system consumes 12 times as much power as it does when using no dummy traffic at all. Now, of course, in cases where constant rate dummy traffic is no option, we have to think of something else. And we came up with this approach named naive exponential dummies, where we say the system draws a random number from an exponential or geometrical, depending whether we're using a discrete time model or a continuous one, from an exponential distribution after each message. And then it waits for this amount of time. And if and only if no genuine message is transmitted within this time, then at the end of the time frame, a dummy message is sent by the system. This parameter of the exponential or geometrical distribution allows for tuning energy efficiency versus privacy. If we, for example, increase the average or the mean of the distribution, then fewer dummy messages are sent. So the time between 2 subsequent dummy messages increases, which improves the energy efficiency, but of course, or as we'll see, decreases the privacy. Now, I won't bore you with any proofs in this talk, but in the paper you can read that we can prove that NED or naive exponential dummies does not provide epsilon delta private communication at all. It's impossible. In general, we also do not have epsilon indistinguishability, where delta is 0. But instead, we have a value of delta larger than 0 in the general case. However, we can prove that for some cases, for example, for single tasks, which only comprise of a single interaction, we can show that net offers epsilon delta unobservability for these tasks and their complements. Now, the proofs are all nice, but the question remains, is net actually feasible to use in a real-world system? And to answer this, we have performed 3 different measurements using the Homatic model from before. We have simulated net using real-world home automation system traffic, and we have calculated values of epsilon and delta and the resulting energy consumption increase, ECI, for those values. The first case is where we have no dummy traffic. Now, this might sound a bit counterintuitive, but when you think about it, if the attacker is not able to decrypt packets and is only able to see message timestamps, then you might have an observation that can be observed when the user performs some interaction, for example, pressing a light switch, but can also be observed when the system performs some automation rule, for example, turning on a light in the morning. Now, the same observation being observed both when the user performs the interaction and when the system follows some automation rule means that this traffic pattern is not unique to this task, which means that values of epsilon and delta actually make sense in this case too. And using this simulation, we could see that using no dummy traffic, the value of epsilon is in the range of 7 to 9, and the value of delta is in the range of 0.7 to 1, where 1 is the worst case, namely that a given observation is so unique that the attacker can learn a definitive piece of information from this. We have then performed a simulation where we set the value or set the parameter of the exponential distribution in a way that approximately 1 packet was sent every 2 seconds. And there we could immediately see that the value of epsilon decreased dramatically. It was lower than 4 in this case. And the value of delta increased even more dramatically from 0.7 to 1 down to a value of less than to the power of -2, so 0.01, less than that. The energy consumption increase was moderate. The system, one system consumed about 20% more power than if no dummy traffic was used, and one system where the difference was more significant, the energy consumption increased by 120%. So it was a little more than double the energy consumption it consumed in the case where no dummy traffic was used. We have then also performed a simulation using a rate of approximately 1 packet per second, and this decreased the value of epsilon to less than 10 to the power of -10. And delta decreased to less than 2 times 10 to the power of -3. So as we can see, when sending 1 dummy packet per second, approximately, those 2 values decrease dramatically. The energy consumption increase is still much, much less than when using constant rate dummy traffic, according to the different models. But the privacy parameters epsilon and delta decrease to a value where it's actually maintainable and offers reasonable privacy at moderate costs of energy. And with this, I would like to conclude my talk. We have seen that constant rate dummy traffic is not necessarily infeasible for some home automation systems, depending on the hardware used. For example, if the system uses regular Wi-Fi hardware, then constant rate dummy traffic might actually be the way to go to achieve perfect epsilon delta private communication, so perfect privacy at moderate costs. And in other cases, naive exponential dummies can provide a tunable compromise between privacy and energy efficiency, and other algorithms that learn user behavior try to adapt this might even provide better results using less energy. Thank you.